Okay, so welcome all again, and it's a pleasure to have you all around. And today we have the pleasure to have Yves, Revaz and Florian Cabot, who will present us the VIRUP, the Virtual Reality Universe project. It's a project that I started more than 2 years ago now, it was a lot of coding, a lot of work, trying to put all together the information we have on the universe into a system that is easy to use and flexible to use, and can basically represent the universe in 2D, in 3D, in VR, in many different systems. So if Revaz is a MER, maître d'enseignement de recherche at EPFL, and Florian Cabot is an engineer and working also at CITAS, and they will present this project. So welcome, and I think Yves, you start.
Good, thank you very much. Thank you, Jean-Paul, for this introduction. So it's a real pleasure, of course, to be here, to have this opportunity to present to you our project called VIRUP, as Jean-Paul said, standing for the Virtual Reality Universe Project. So we share the talk together with Florian, who was a major actor in this project. How is the universe beyond the Earth? This is certainly a question that all modern and ancient civilization asked, but it's only very recently that we have a good understanding of how it really looks like to very large scales. In fact, for centuries, humans were looking at the sky with their naked eyes, with obviously a pretty low understanding of what was going on there. It's only 400 years ago that Galileo Galilei, thanks to a homemade refractor telescope, looked at objects beyond the Earth and obtaining detailed information on, for example, the craters on the surface of the Moon, the Jupiter telescope, the Saturn ring, and so on and so forth. From a theoretical point of view, it's only 100 years ago that, thanks to the amazing work of Albert Einstein, we got a mathematical framework that allows us to understand the universe as a thing. And this really turns, at this point, cosmology to a science. Anyway, now when we combine theory with observations, I think we pretty much understand our universe. If we assume that it is isotropic and homogeneous at very, very large scale, we can describe it from a mathematical point of view. We know that it is expanding. In fact, it's not only expanding, it is accelerating. We know that it is more or less 13 billion years old. But it's only very, very recently, I would say, last 20, 30 years, that we understood that the universe was very complex. I mean, the way galaxies are distributed in the universe at large scale is very complex. As you can see here in this blue point, which correspond to kind of slice of portion of the universe, and you see that galaxies obtained by different battery of telescopes are not spread very homogeneously. They create filamentary structure, void, and so on and so forth. Now, if you combine the theoretical model we have of our universe with powerful simulation, you see that you can recover this very nice and complex large-scale structure. This is the red point you obtain in this figure. And the very important point to make here is that theory is able to reproduce this large-scale structure. And now we have a very good understanding of how our universe looks like over very large scales. And this is, in fact, exactly the goal of VIRUP. So the goal of VIRUP was to provide anyone, to a very broad public, with the most modern view we have of our universe. And a very important point, and I will insist on that, we wanted to combine not only direct observation, but also we wanted to combine information that are obtained through numerical simulations. So And the way we wanted to diffuse this understanding of our universe to the broad public was through cutting-edge visualization technology, which is the virtual reality. So after this brief introduction to VIRUP, let me go to the outlines of the talk today. So I think it's important to give you a little bit of information on how we, of the history of VIRUP. And then we'll really enter providing you with much more details. What is the real goal of VIRUP? What is the challenge we face? What is the content of VIRUP? And I will also talk about the fact that VIRUP may be used not only in virtual reality environments, but on very specific virtual reality environments that I will present further. And finally, I wanted also to mention that VIRUP may now be used to provide outreach material. I think this is an important point. So, a short history of VIRUP. In fact, all these projects started years ago from a real need to visualize results of simulated galaxies. So, at the laboratory of Astrophysic, what were, beside observations, we are interested in understanding the formation and evolution of galaxies that we produce through computers. So we use battery of computers, and as you know, computers are only dealing with 0 and 1. But at some point, we want to understand what are the output of the simulation. So we have to turn 0 and 1 into scientific content. In particular, we can create images. And if you do understand how to create images out of the 0 and 1, it's easy to understand that it's possible to create another image, just shifting the camera. So we can obtain two images, obtained from different point of view, and combining both together lets you observe your simulation in stereo. And if you do understand how to create imaging, it's easy to understand that you can create multiple images showing, in fact, the evolution of the system you are interested in. You can do that in stereo. In fact, when we are doing that, we realized that those movies were quite appealing, could be used to diffuse our research to a very large public. And in fact, we started doing these kind of things more than 15 years ago. In 2005, we installed the first so-called geo-world system at the Synra Observatory. The system, which is reproduced here, consists of two beamers. You polarize the light, you project that into a special screen, and you can watch evolution of simulations in stereo, wearing special glasses. So that was our first experiment, and it was pretty successful. A few years later, in 2009, that was the International Year of Astronomy, and at its occasion, we installed a similar geo-world system at the Observatoire de Ginevra, Observatoire de Solernay. But this time, in addition to provide public with our own video, we used the software, which was called Celestia, and we hacked it to render 3D images. At the same time, we also realized, combining these different images, a first short 10-minute long 3D documentary, which was called Voyage dans le Cosmos. It has been broadcast at many different places, the Salon du Livre in Geneva, au Grand Palais à Paris, as well as the Comptoir Suisse in Lausanne. So we reached really quite a lot of people. 2014, that was, maybe some of you remember, but that was the inauguration of the Swiss Tech Promotion Centers, and we have been invited to show our 3D movies, and we realized a new one, a slightly extended version of our documentary. It's called Un Voyage dans l'univers. So we are really happy with this very positive experiences. We really wanted to go beyond that. And of course, going beyond that means maybe using another technique. And why not dealing with virtual reality? So this is what we did. In 2017, we started this project VIRUP, and we managed to make it real thanks to different sources of funding. And we thankfully had the Swiss National Science Foundation, as well as some the EPFL, who provided us with some seed money for interdisciplinary collaboration. By the way, we started a collaboration at this time with the FM Plus and LG lab. EM Plus, that the laboratory of Sarah Conderline, working on experimental musology. Good. So what is VIRUP? So VIRUP is first a project which articulates around a brand new software. The software provided a completely new virtual reality environment. The software, by the way, as the name of the project, is VIRUP, and it is an open source C++ OpenGL Qt software that has been completely written by Florian Cabot. So you can freely download the software. You have the link here on GitLab. You can also go to this other link, go.epfl.ch/VIRUP, where you find all the information on the additional links. So this project articulates around software, but part of the project, we wanted also to create outreach content, and I will talk later on the realization of movies and documentaries. What was the goal of VIRUP? So it was really to immerse people through the different scale of the universe, not only spatial scale, but also time scale. So you can freely navigate through large data sets at different epoch of the time, right? And again, I insist here that these very large data sets correspond both to different sample of observations, but also output of heavy numerical simulations. So this provide really, the goal was really to provide is the most up-to-date understanding of objects in the universe. Just to give you some idea, the kind of object you can find, of course, is solar bodies, all the planets, the orbits. We have also added artificial satellites. We have all the recently observed Gaia stars, so that's several billion of stars. We have a model of the Milky Way, we have a model of the local group, and then beyond the local group, we have the numerical model, where we combine both the numerical model of the distribution of galaxies in the universe as well as observed galaxies. In total, this is really something interesting. We cover, in terms of spatial scale, up to 27 orders of magnitude. So we count that from the, if you look at the more detailed stuff you can see in VIRUP, that's of the order of centimeter, but we can also have a complete view of the universe up to its extent. So we consider here the extent of the universe, and the extent of the observable universe, so something like 100 billion light years. So initially, we designed VIRUP to run on what we can call sometimes gamer virtual reality headsets, or sometimes it's called head-mounted displays. As you can see here, this person has this virtual headsets. And so the idea was to provide this new environment and make it use with these devices. But as I will show you, we went beyond that, and it's possible to run VIRUP on a variety of other visualization systems. When you are using these VR headsets, you can travel through data thanks to, well, you can interact with the data thanks to this hand tracking system. But if you are not familiar enough with that, and it turns out that it is very difficult sometimes for people to really use that, it's possible to organize what we call semi-guided tools. So we script some sequences, and the person may simply walk around the object and so on and so forth. Okay, so this is a picture that shows you how this works. And I wanted to insist here on the fact that one of the goals was really that the users discover the different scale of the universe, to apprehend the different scale, to understand how the scales are different. So one of the originality of VIRUP is it allows to scale the user to the objects who wants to study. For example, here you see the Earth, which has a size of more or less 1 meter. It means that the room where the user is experimenting this virtual reality experiments is about correspond to the size of about 30,000 kilometers. Now, if you jump to galaxy, for example, think that the user will have more or less the size of the galaxy, and the box say differently. We have to cover a volume in space of something like 100,000 light years. You can go that up to really big portion of the universe, where here the box has a size of 100 billion years. Okay, before showing the, I can now give the floor to Florian.
Yes, thank you, Yves. Thank you, Jean-Paul. So I will present to you what we can show with VIRUP and how I managed to make it. So I will show a bit of the algorithms I've used. It will be high level, so hopefully everyone can follow. And I will start with the biggest of them all, which was how to visualize large data sets. So the two biggest ones we have are the illustrious TNG data. So this is a cosmological simulation. And we also have, as Yves mentioned, the Gaia data. So all the stars you see on this image are from the Gaia observations. And the dust patterns you can see are really from the Milky Way and from the Gaia data. So the Gaia data is 35 gigabytes when you only account for space data and luminosity data for 1.5 billion objects, and the same for illustrious TNG data, but it's half a terabyte of data for 30 billion particles. As Yves mentioned, we wanted to be able to visualize this on the consumer VR headsets, which now are about 8 megapixel resolution, and they render at 90 frames per second. So to do this, you can't just show all the data at once. So you have to split the data into chunks. So this is done with a data structure, which is called the knob tree. So you start with a purple cube, which contains all the data, and then recursively, for a given cube, if it contains enough data, you split it into 8 cubes. So here the purple cube would be split into the red cubes. And the purple cube would still contain a subsample of all the data. So that if we don't want to display everything, we can just display the subsample, or if we can afford it, we can display some of the data contained in the subcubes. So every time you render, you ask a cube, do you render a subsample of yourself, or do you render the subcubes that are contained inside of you? But you have to do it based on a criterion. So this criterion is compared to the diagonal over distance to the camera of the cube. So the bigger the cube will appear on screen, the less likely it is that it will render its subcube. Or if it appears very tiny on the screen, you only have to render the subsets of the data and not the whole data. So now we have to fix this criterion, C. And to do that, as VIRUP will be, is used over quite a few different range of hardware, we can't decide beforehand. So we use a tool from automation, which is called the PID loop, which ensures that the frames per second rendered by VIRUP is fixed at 90, regardless of the hardware power. So VIRUP has a current FPS counter. We fix a target FPS, so we get an error, and this error gets inputted to a function of which has 3 parameters: P for proportional, I for integral, and D for derivative. And by fixing those parameters correctly, evaluating this function will give us a delta C, so a change in C, so that VIRUP renders at the target FPS. Then the second challenge is the fact that, as Yves mentioned, there are a lot of different scales to render at once. So we get into floating points error territory. This means that when you want to have a certain resolution at one point, which is very precise, here you have 2 points that are separated by a very tiny amount. When you deal with variables on computers, you can't store all the precision, so you have to truncate the numbers at some point. Just for the sake of argument, let's say that we keep only 2 digits. You see that there is a problem here because both those numbers will be stored as the same value. So what you need to do is to always shift the origin the closest to the most detailed place you want. So here, if we shift the origin to 2.5, the number will be stored as those, and if you keep the 2 digits, they are correctly considered as 2 different numbers. So the solution applied to VIRUP, so this is a 2D example, but of course we work in 3D, that for the octree, we always consider the origin to be the closest data point to the camera. So every time the camera moves towards a different point, we have to shift the whole coordinate system so that the camera really can get as close as possible to any point. And for planetary systems, this is a star. Those are 2 planets, and there are 2 moons here. So the camera position would be stored related to the closest object to it. So here it would be this moon. And the position of this moon would be computed relative to the closest parent to both moons. So it's never stored as a position related to the star, unless, of course, the star is the closest parent. Then we also have some volumetric rendering in VIRUP. Here you can see a simulation of the Milky Way. So we use the octree to render the stars, but you can see there are more than stars here. And if we go closer, we can see that we have some red patches, which is hydrogen alpha emission. And there is some absorption by dust. And to do that, we need another data structure than particles. We use volumes. So really, you can picture them as 3D images, which contain values for emission or absorption. And to render an emitted patch to the camera, we trace a ray to the bottom of the limit of the volume. And then you go step by step through the volume and you sum up all the emission. And for the absorption, whenever you render a star, you start from there, and then you step back to the camera and integrate all the absorption to reduce the luminosity of the star. Of course, when you have the H-alpha emission, you have to combine both emission and absorption so that the H-alpha emission is hidden by the dust. Then I will talk briefly about the Kepler orbit interpolation. So the motivation for that is that we really want to have the most accurate positions of objects in the solar system at all times. So this is an example of the solar eclipse that will happen in April 8th, 2024. So if you want those eclipses to be accurate, you really have to have all the positions in the solar system accurate. So to do this, we get the positions from the NASA JPL Horizons tool. But VIRUP is an offline tool, so we can't just store all the NASA database in the computer, of course. So we have to be a bit more clever. So you would think that you would only have to store the positions of the bodies at some key points, and then you can interpolate linearly through those points, and this gives you the left results with the red points being the data you got from the NASA server. But you see, the bodies will follow some edges like this, and it won't be good enough. So what you do is, instead of storing the positions of the body, you store the orbital elements, because the orbital elements tend to vary way less than the position or the velocity. So doing this, you only have to store one data point per day, even for the ISS, which does 16 revolutions per day, and it still will be very accurate. For example, the ISS, I noticed it can drift at the middle of the day from 30 seconds to 1 minute compared to the real position. Then a topic which is very similar to volumetric rendering, but a bit more complex, is the atmospheric scattering rendering. So when you have atmospheres to render, you really can't do simpler than this, and it's quite complex actually. So this is an example of an exoplanetary planet in VIRUP, an exoplanet, which has an atmosphere. And this is a view from the Earth in VIRUP, and you can get down to the surface and get some sunsets, for example. So it works very similarly to volumetric rendering, but you have to take into account the in-scattering of the lights coming from the sun. And so the camera is at the top left here. So you trace a ray, like for any volumetric rendering method, that goes from one point of the atmosphere to the point closer to the camera, and you sum up some quantity over this ray. Actually, if an object was behind here, you would have some incoming light already at this point, but if there is no object behind, then it would be pitch black. And then for every point, you get a ray from the sun general direction, which is outscattered, which means this ray loses some light on its path to this blue path. And it's so for every ray coming from the sun. And of course, the blue ray also loses some light along its way to the camera. So you really have a double integral here, which is very expensive to compute, because also those are non-linear evaluations. So this is the naive algorithm, but of course you have to make a lot of optimization for it to work in real time. So I used the implementation from this paper, which covers all the optimizations. Then a very simple topic, but which can be overlooked if one just uses a pre-built renderer to do some global illumination and shadows. So of course, this is an eclipse image again. And now I will talk about the shadow of the moon being displayed here on the Earth. Here you can see from the Io moon its shadow onto Jupiter. And also regarding global illumination, you can see the light from the Earth lighting the dark side of the moon. So the left side of the slide deals with the shadows. So a very simple observation is that it can actually be solved geometrically. In a typical renderer, you would use shadow mapping and stuff like this, which is very expensive. But here, because planets are almost spheres, you can do it geometrically. So from any point on Earth here, if you want the shadow of the moon to be displayed on it, you have to wonder, what does this point see in the sky? So you project the sun and the moon onto a plane, and here you have a 2D, very simple geometric problem, which is how much of the sun is covered by the moon. And then for the illumination, here, if we want the light from the Earth to light the moon, you first have to compute how much light does the Earth get from the sun, then how much is reflected towards the moon. If you take into account the fact that there is an angle and not the whole disk will cast some light, and then you can light this part of the moon. Of course, if there is an object way closer to the Earth than the moon, for example, if it would be the ISS here, it will only see a small part of the disk. So here, for example, the ISS will get 100% of the luminosity from the Earth. Then a quick look into human vision and the realistic luminance in VIRUP. So this image shows a lot on this topic. So on the very left, you can see some sunlight way past the horizon, which you should see has some colors. This side, which is very dark, has some city lights, and here it is lit by the light of the moon, coming from the moon. And you can see that it's all gray. Actually, the light coming from the moon makes a similar color pattern in the atmosphere than the sun, but we don't see it with our eyes because the light is very dim. And with very dim light, the human eyes can't see the colors anymore. So this is simulated in VIRUP. And all of this is possible because we keep the physical light values as much as we can. And only at the very last step of the rendering, we transform from physical lights to rendered light in RGB. So to do this, we use a process called tone mapping, which is going from physical to RGB. And we wanted to use a model for this that is close to human vision. So that's why we can see the moonlight in gray, and also by keeping all the luminosities physical, we can have very realistic comparisons between the luminosities of different objects. So here we can really see the Andromeda galaxy and some Hipparcos stars, both lit the way they should be related to each other. And finally, the last challenge I want to talk about, this one will be brief, is the fact that VIRUP, because it's not only VR, and we will talk a bit about that right after me, it has to render on a lot of different hardwares, and some can be distributed into different computers, and each computer can also have several screens. So this would be a typical setup VIRUP would run on at the EM+ laboratory. So when running on a single computer and several screens, like only this, for example, we have to compute as much as possible only once what's needed to be computed before displaying to both screens almost at the same time. And then when you have two computers, you have to communicate over the network. So both computers need to have the data, and both need to be the whole pipeline of processing the data and rendering it. And the only data that's really communicated here would be the camera position and some visualization parameters like luminosities and opacities and yeah, this kind of stuff. So on this topic of multi-screen over the network, I think I will let you take that.
So yeah, yes, as explained before, VIRUP has been first designed to work on VR headsets, classical gaming headsets. But of course, you can download it and use it, compile it, and use it simply on simple laptop and looking at the data for 2D screen. It supports also 2D screen. Well, when you are using, by the way, a laptop and controls VIRUPs for a keyboard, mouse, we can also now use gamepads. When you are in the VR environment, you will use tracking system. Anyway, so that's what I call a standard system. They are fully supported by VIRUP, but thanks to a collaboration with the experimental museology lab from Sarah, we go further by using what I mentioned here, advanced visualization system, and I will show you three of them. VIRUP may be used in a 180-degree dome, as you can see here. So there, in fact, you project on an hemispherical screen the images provided by VIRUP. For that, you need 2 mirrors, and you obtain a quite high resolution of 4,000 by 4,000. Here you can see, by the way, so the dome with an image where you see the International Space Station within the Earth. By the way, well, this is another example of the same device. By the way, it's very comfortable to do. When you have sofa, you can lie down there and just the scan. Another of the system is the so-called Archaeology. Here you use 2 mirrors, one that will project on the wall, and another one project on the floor. Both mirrors are 3D, so you can experiment a very nice immersion there. You see these 2 persons that are looking at the Earth here. You see the object in stereo. I have another picture here that shows you can also interact with the data for and finally, it has been important with this amazing system, which is called the Panorama. Panorama, the gigantic screen, the 360-degree screen, with a diameter of 9 meters, and the height of the screen is something like 3.5 meters. Here, the resolution which is obtained is amazing. It's 18,000 times 2,000. For that, you use 5 beamers. They are all 3D 4K beamers. So you can really nicely walk in this room. The interesting point is that you can be up to 10, 15 people. You will have a guy that will explain you what to look at, and so on, of course, and everything is, of course, in 3D. So you have to feel the distance. Another view where you see all the different pictures. You can really vary the constellation, the orbits, and so on. Good. I would like to finish by talking very briefly about one of the goals of VIRUP. One of the goals was to provide outreach material. And in fact, thanks to a very nice Python interface that Florian implemented in VIRUP, we can script any kind of scene and script sequences. By putting all these sequences together, we can create movies. By the way, VIRUP supports many different formats, so you can create sequences in 2D, of course, 3D, 180-degree, 360, or more complex formats in virtual reality, 3D VR, 180 or 3D VR, 360. So benefiting from these features, we created in 2020 the first 4-minute-long documentary. That was done at the occasion of the eBOSS data release that provided the most complete survey of galaxies, with about 4 million galaxies. So we created this short documentary and it received a very large success. It has been viewed by more than, we know that it has been viewed by more than 1 million people. It is some 300,000 views on YouTube, as well as more than 1 million views on the EDB platform, the Chinese platform equivalent of YouTube. So if you are interested, by the way, well, either you Google or you follow this link. So thanks to this very nice success, we decided to do another documentary, slightly longer, that was in which we travel really to a different scale in the universe. This one was called Archaeology of Light, and we created it last year in September 2021. And it received more than 100,000 views on YouTube. And that's the VR version we received, that, which is quite amazing to me. That there are many people that enjoy it, they enjoy the virtual version. By the way, it has been contains both French and English voices. This is a screenshot of the theater of Archaeology of Light. Give me the opportunity, by the way, to thank the whole team that worked hardly to realize this movie. Hilary, Century, and Lardo, and Luciano, Austin Film, George Bernardes, as well as Adrian. We are really proud that, in fact, this documentary has been shown in one of the biggest dome existing in the world, 3D dome, called the Synra Dome of the Science Museum of Tokyo. And it was, so the diffusion of this movie was planned initially to last 2 or 3 weeks, and finally they asked us to diffuse it for another month. It was pretty successful. Let me finish this presentation by telling you that if you are interested in VIRUP, you want to know more and see how it really looks like, there is an ongoing exhibition now at the pavilion of EPFL called Cosmos Archaeology, and there you can experiment VIRUP. So there is a demo where you can travel to space using a 6-bit controller, and we also diffuse our 20-minute long documentary. So we stop there. Thank you very much for your attention, and we can take questions.
Thank you, Yves, and thank Florian. Next question in the room.
Well, yeah.
Yes.
There's something I really understand. So basically, it's the software that you made.
Mm-hmm.
But if you want to add things, like if you discover something new in the universe, can you just update it so easily and we download the new version, or it automatically updates, or you have to manually go and change all the things?
So it's not automatic, but it's simple, at least for, I mean, for physicists, it would be simple, maybe not for the general public. Yeah. But all the data that's displayed in VIRUP is actually an input. So it doesn't really know in advance that Gaia exists or even the solar system exists. So it's all in files that are inputted in VIRUP. So you could put any astrophysical data.
Okay. Okay.
Any other question here? Yes.
So a given user that has a VR headset is able like to zoom or dezoom or navigate within the universe, or is it like a more advanced feature that you would have a script so that it's done automatically?
No, he will be able to do that. So if you download the software, it's implemented. So if he has, well, you need to, well, in the VR environment, you really need to have the controllers of the hand tracking system. If you have that, indeed, you can travel fully to space, zooming over the different scales. Yes. And you can benefit also from the Python scripting system.
Yeah, because you can get lost easily.
Yeah, of course, this requires a little bit of training. Mm-hmm. So this is why, by the way, when we show VIRUP to open days as we have for scientific EPFL, we decided to go for the scripting to script sequences. Within 2-3 minutes, I mean, people are not able to really use VIRUP and efficiently.
question regarding the FPS. I'm not specialist in VR headset and stuff, but 90 frames per second is quite high, I would say.
And they can go even
higher. So it's fixed, and there is no way, because I guess it could be more
Yes, so
efficient with less frames per second. So
yes, you can go with a few less frames per second, but the lower you get, the lower you go, and the dizzier the user will get. So you really want to hit that mark.
Yeah.
But I mean, the driver would let you display 1 frame per second.
but I mean, like 60 is already quite good.
Depends on
I
the
would have
people.
guessed.
Some people don't really mind, and some they wouldn't bear it so much. And now recent headsets. I mean, I've heard of people that even for whom 90 frames per second is already too low. And now some headsets are going 140 or something, and those people can use those headsets now. So you really want to go high.
By the way, if I may comment, this, I mean, if you really benefit from VIRUP, you really need to have a quite powerful gamer hardware. Yeah.
Yes. So
We could install it.
Sure.
I don't know why I didn't think of this before.
Yeah, indeed.
Yeah, I'll do that.
Possible to run VIRUP on would it be possible to run VIRUP on a very powerful computer or a cluster of computer, as we have a thing in EPFL, and then stream the data to clients headset?
So that's one thing I wanted to try just before the summer, but didn't have time to. I think it's very hard to do. Like you would need some software that would stream some VR data over the network with very low latency. I don't know if it exists. I think it does, but maybe you need, I think, to use some Amazon servers or something. Maybe possible, very hard probably, but it can't do it right now. But you can render some movies on a server.
Other questions? Have you got some users' feedback that download VIRUP and ask you questions? I mean, have you had some interaction with users or not yet, or not?
It depends on how you define user, but I mean, yeah, a lot of people have tried it already. Just at the observatory, for example, I have a lot of positive feedback. Then for people who used it themselves, so already also at the observatory, a lot of people have tried it by themselves, so they told me some feedback. And then from the internet, not that much, I think, about 10 people.
But do you think because it's too complex, or because what's the limiting factor, if there's one? Maybe it's also people don't know, so they never try.
Yeah, I think it's quite an important factor. And also maybe the website is not that clear about how to get it. Could work a bit on that. Like just click this button.
Yeah.
And if we don't want to use VR, so what we see is just the same thing that the video, the Archaeology of Light video.
Yes.
And the traveling with the
yes, so you can do all the interactions that are possible in VR, but with keyboard and mouse or a gamepad. And instead of a VR projection, you would only get to the regular one.
Good. Yeah, we should definitely.
Are there questions online?
No, but there are people saying thank you for the good presentation, and from students from Gymnase Provence. I don't know if you. I don't know what they say.
Okay.
So thank you very much.
Yeah. Thanks a lot.
Thank you for the invitation.
Okay, so thanks again for joining online and here, and we'll come back with another presentation in a few weeks, right?
Next Monday.
Next Monday, in fact. Okay. Thanks a lot.
Thank you, everyone.
Have a good evening. Bye.